You know that feeling when you look at a scientific graph and your brain just shuts down? Well, today, we're going to change that. We're taking on a university chemistry exam question, but we're not just going to crunch numbers. We're going to tell the story of a chemical reaction, one drop at a time. Let's break down a titration curve.
So how in the world do chemists actually watch a reaction happen? I mean, you can't just peer into a beaker and see atoms doing their thing. Instead, they use this really clever technique called titration. You add one chemical to another, drop by drop, and you track something, in our case, the pH. It's basically like getting a live, play-by-play commentary of a chemical game.
Okay, let's get into it. Our specific challenge today comes from question 2 of a 2016 university chemistry exam. We're going to do this titration virtually, step by step, not just to find the answer, but to really understand the chemistry that makes the graph look the way it does.
All right, every good story needs its characters. In our beaker, our main character is 30 milliliters of ammonia. It's what we call a weak base. And the chemical we're going to be adding, drop by drop, is hydrochloric acid, a strong acid. This classic matchup, a weak base versus a strong acid, is what sets the stage for our entire story arc, or, our titration curve.
Now, before we start plotting anything, we need to know the one single rule that runs this whole show. There's one fundamental reaction that happens over and over again, every time a drop of that acid hits the solution.
And here it is. It's actually pretty simple. The ammonia, that's NH3, grabs a hydrogen ion, the H+, from the acid we're adding. When they team up, they form ammonium, or NH4+, which is what we call the conjugate acid of ammonia. That's it. That one little transformation is the engine behind every single pH change we're about to see.
Okay, now for the main event, we're going to go on a little journey through this reaction. We'll stop at 3 super important moments to figure out the pH. Taking it step by step like this will give us the key points we need to actually build the graph and see the whole story.
So, let's start right at the beginning. Before we've added a single drop of acid, what's the pH of our ammonia solution just sitting there by itself? This is our starting line, our baseline for the whole experiment.
Now, the most important thing to remember here is that ammonia is a weak base. That means, unlike a strong base, it doesn't completely break apart in water. It kind of dips its toes in, setting up an equilibrium. And the strength of that reaction is measured by its Kb value. A tiny Kb like this one tells us it's only a little bit basic, but it's definitely not neutral.
So you run the numbers, and boom, we get a starting pH of 11.28. That's our first data point. And it makes sense, right? It's way up there in the basic range. Let's lock that number in our minds.
Okay, next stop on our journey. We've added 20 milliliters of acid. Now, that's not just some random number. The whole reaction is going to take 40 milliliters, so this is the exact halfway point. And let me tell you, in titration, the halfway point is a very, very special place to be.
So what makes this spot so special? Well, we've created a perfect buffer. Because at this exact moment, we have equal amounts of our weak base, the ammonia, and the conjugate acid we've been making, the ammonium. And when you have both of them together, they work as a team to fight off big changes in pH. It's kind of like a chemical sweet spot.
And the pH at this magical point is 9.25. And here's the really cool part. At the halfway point, the pH is always equal to the pKa of the conjugate acid. So you can see the pH has dropped, but it hasn't crashed. That's that buffer doing its job perfectly.
And now, for the climax of our story, the equivalence point. We've added exactly 40 milliliters of acid. This is the moment. The amount of acid we've added is now perfectly equal to the amount of base we started with. The original reaction is officially over.
So think of this as a complete identity crisis for our solution. The original ammonia we started with, poof, it's all gone. It's been completely converted into the product, ammonium. And because ammonium is a weak acid, our solution is now going to behave like an acid. The roles have totally reversed.
And the resulting pH is 5.16. Whoa, look at that drop. We went from basic, blew right past neutral, and landed squarely in the acidic range. This massive, steep plunge is the classic signature of reaching the equivalence point. So, we did the hard work. We have our 3 key data points, the beginning, the middle, and the end of the reaction. Now for the fun part. Let's turn these numbers into a picture and watch the full story of our titration come to life.
Okay, here's our canvas. We've got the pH scale running up the side and the volume of acid we've added along the bottom.
It's time to put our points on the map and see what shape starts to form.
First up, point number 1. At 0 milliliters of acid, our pH was way up there at 11.28. This high starting point is our first big visual clue that we started with a base.
Next, we move over to 20 milliliters, our halfway mark, and the pH has dropped to 9.25. See how this part of the graph is starting to look a little flatter? That's the visual proof of that stable buffer region we were talking about. The pH is really resisting change right here.
And finally, bam! At the 40 milliliter mark, the equivalence point, the pH just plummets all the way down to 5.16. You can already see that dramatic, steep drop taking shape right in the middle of our graph. This is the visual climax. And now, when we connect the dots with a smooth line, there it is, the classic S shape of a weak base being titrated by a strong acid. This isn't just a bunch of points on a page anymore. This curve is the complete story of our chemical reaction, from start to finish.
So, we built it. But what does it all mean? Let's do a quick recap of the story that this simple S-curve tells a chemist, just by looking at it. That high starting point, it screams I started with a base. The flattish section in the middle, that shows off the powerful buffering effect. That insane vertical drop is the unmistakable signal that you've hit the equivalence point, the reaction is done. And the fact that this point is below a pH of 7, that confirms that the thing we made, our product, is actually an acid. It's all there, in one elegant curve. So we managed to take a tricky chemistry problem and translate it into a visual story. It kind of makes you wonder, right? What other complex stories, whether in science or just out there in the world, could we finally understand if we just knew how to read the story hiding in their graphs?